now that we've seen some of the results of the special theory of relativity in terms of measuring time, more specifically time dilation, the time dilation effect, let's turn now to measuring length and see what we can find out about that, especially measuring length of a moving object. And so here's our situation. We've got Alice and Bob again. Here is Alice. She is stationary. This is her ship or just some platform or something. We're just going to focus on one clock of hers for this example. And then here's Bob on his spaceship going by at some velocity v. We've drawn a number of clocks for him just to remind ourselves that actually in all the things we're doing, we always have that lattice or grid of clocks all synchronized. So in Bob or Alice's frame of reference, all Bob's clocks are synchronized. He thinks they're in good working order. Alice, we're just showing one clock for her, but she'd have a whole lattice of clocks as well, and they would be synchronized for her. So, but remember, of course, as we showed earlier, Alice would not see Bob's clock synchronized and the other way around. So that will be a key point here in a few minutes. But let's get back to the example. So Bob's going to fly by here at some velocity v, and Alice is going to measure the length of Bob's ship as he goes by. And so to do that, when the front of his ship reaches her clock here, she'll take a photograph. It's our photograph principle again. And she'll see the time on her clock. We'll call that T sub A1. In other words, Alice's clock, time 1. And the photograph will also include the time on Bob's leading clock here, TB1. TA1 and TB1. And then that's the first snapshot. Bob's spaceship travels on. And then when the end of Bob's spaceship reaches that point, another photograph will be taken. By that time, Alice's clock will be at T sub A2, okay, her clock at time 2. And Bob's clock will have some TB2 on it as well, time T, B, number 2 there. So, how then does Alice get the result for the length of Bob's ship? Well, it's simply, we know that it's going to be essentially the distance traveled here. We know Bob is traveling at a constant velocity v. That's what Alice sees him doing. He will travel a certain distance in that amount of time, represented by essentially the end of her ship coming to this point here. And so that will be the length of his ship as, start the clock here, wait until you see the end of the ship go by, stop the clock as we did right here in our second snapshot. So TA2 there, and it's very simply, you take the velocity of the ship and multiply by the elapsed time between the time that you see the beginning of the ship, the front of the ship, and the back end of the ship. So Alice will say, okay, I've got a result. And the result is the velocity times the time difference, T sub A2 minus T sub A1, just the elapsed time between those 2 points on her clock. So T sub A2 minus T sub A1. And we'll just rewrite that as we've done before using delta. So this becomes V delta T sub A, the elapsed time on Alice's clock. And then Bob says, well, I can also get the length of my ship from our little experiment here because I've recorded, the photographs record TB1 and TB2. So that's my elapsed time in terms of my clocks. I know I'm going at a velocity v, or really, you could think of it from his perspective as he could imagine he's at rest and Alice is going by. So he measures when Alice is at the front of his ship, TB1, and how long it takes Alice to get to the back of his ship at TB2. He's going with velocity v this way if he thinks he's at rest, and Alice clearly is going with velocity v that way. And therefore, again, the length of his ship is going to be v, the velocity, times the elapsed time on his clocks, TB2 minus TB1. So TB2 minus TB1. And again, we'll just rewrite that using our delta symbol. So it's V delta TB. And they get back together again, and they compare results. And Bob says, hey, you didn't get the same length as I did. What's going on here? You screwed up, right? Right? Why did you mess up your result? Well, as Bob considers it, he says, hey, you know what, Alice? Your clock is running slow. You know, my clock is in perfect working order. We have identical clocks. But remember, from our time dilation effect, moving clocks run slow. And so from Bob's perspective, he's at rest. Alice is actually moving that way compared to him. And he compares the ticking of her clock to the ticking of his clocks, the elapsed time. He says, Alice, your clock is off. Now, I'm sorry to say that, but your clock is off. That's why you're getting the wrong answer here. And my answer is correct. That, whatever the numbers we could put in, v times delta t sub b. And obviously we're assuming v is fairly close to the speed of light to get any effects here, as we shall see. But so that's what Bob is saying. Bob's saying, hey, my answer is right. You got the wrong answer, Alice, because your clock is not in working order. It's running too slowly compared to my standard clocks, which are in perfect working order. Well, what's Alice's response to that? And actually, a few minutes ago, we hinted at that. So you might want to think about a minute from Alice's perspective, what's going on? What does she point to in terms of Bob's measurement of the system, where she says, it's not my problem, Bob. You're the one who messed this up. So think about that a minute. If you want, you can pause and puzzle that one over a minute. But here's the answer. The answer is that, remember our little phrase we used when we did analysis like this with moving clocks, especially on spaceships? Leading clocks lag. Remember that? Leading clocks. Leading clocks lag. So as Alice looks at Bob's clocks here, if she were to look at all of Bob's clocks at the same instant, so say at this instant in time, we not only take a photograph here, but we have another photographic device out here. Remember, we imagine Alice having a whole lattice of clocks, so we can take a photograph any place along that we want and compare times with other clocks and locations. So take a photograph. When this photograph here goes off, she'll take another photograph simultaneously here. What will she see on this clock of Bob's? Well, Bob's clocks are moving toward her like this, past her like this. As we showed previously, leading clocks lag. She will see this clock behind this clock here. And therefore, she'll say, Bob, your clocks aren't synchronized. Notice that in Bob's measurement, he has to use two clocks. Alice is only using one clock. Bob is passing by her like that. To measure his own length, Bob has to use this clock and that clock for the length of his spaceship. And Alice is saying, I'm sorry to say, Bob, but your front clock here is not synchronized with your back clock. In fact, it lags by a certain amount. So that when this clock here, when this photograph is taken, this clock is actually further on in time at that point. And that's why you got the wrong answer. My answer is correct. So, what's going on here more quantitatively? Okay, so both of them are complaining about the other's results. And basically, in a sense, they're both right. But again, it's the relativity of simultaneity in terms of synchronized clocks, the relativity of timekeeping with time dilation, which we'll get to here in just a second, and as we'll see, the relativity of measuring length when things are moving. So here are the two results we got. Okay, Alice is getting this result, Bob is getting this result. They would turn out to be different answers if we looked at them. And the reason they're getting different answers we just explained. Again, Bob is saying, hey, Alice, your clock is running too slow. And Alice is saying, Bob, your clocks aren't even synchronized, so why even bothering to make these measurements? So let's look at these results a little bit further, because we now can apply. And, let's see where we're going to do this. Let's just remind ourselves up here for a second. Remember our time dilation result. And our time dilation result, from Bob's perspective now, he would say, in the elapsed time for Alice is 1 over gamma his elapsed time. Because from his perspective, so for Bob, From his perspective, Alice is moving. So let's start with that. So as he analyzes Alice's result here, I guess we will need some more room here. So you have the pictures, and I forgot to mention, but it should be obvious. The handout has this diagram on that, so you don't have to redo it. In this case, we just have this one, or really two diagrams here. Not too bad to reproduce those. But let's look at then these results here. Okay, so we get LB. This is Alice's result for the length of Bob's ship. LB Alice, we said, was V delta TA. But Bob is saying, that delta TA, that time difference, is actually 1 over gamma delta TB. So this becomes V times 1 over gamma delta TB. In other words, remember, Bob says, Alice, your clock is running too slowly. Therefore, the elapsed time will be less. Remember, gamma is greater than 1. So from Bob's perspective, this is his explanation for why Alice's clock is running too slowly. It's running too slowly by a factor of 1 over gamma. So we put that in here. But look what we get from this. We just rearrange the terms. We'll have 1 over gamma in front. Let's put that in front and move the V over this way. V delta T B, but V delta TB is the length of Bob's ship from Bob's perspective. So this becomes 1 over gamma LB Bob. And now we have a nice little equation. So we'll write this down here. LB Alice equals 1 over gamma LB Bob. So now we have a nice little equation for measuring the length of a moving object in terms of the different lengths different observers will get. Bob gets a certain length LB for his ship, and as far as he's concerned, he's at rest. So he can just lay out his ruler there and measure it if he has to. Alice, though, as she sees Bob's ship flying by and trying to do the measurement with her clock and her knowledge of Bob's velocity, gets a result that's 1 over gamma Bob's result. Now remember, gamma is greater than 1 here, so her length is going to be less than Bob's length. Earlier we didn't specify that because we couldn't necessarily tell just from the results there which one was less and which one was more. We could see they were different. Could analyze that. But here's the quantitatively how they're different. That when Alice measures Bob's moving spaceship, the length of it, she'll get a result that's 1 over gamma times the length of whatever Bob gets just from being his own spaceship at rest as far as he's concerned. And note that we can actually see a similarity here between our time dilation equation and this is known as length contraction. Length contraction. In other words, moving lengths, if they're measured, contract. They're shorter than they would otherwise be by this 1 over gamma factor. So remember, before to get up gamma around 2, we have to get up to about 0.99 speed of c, right around in there. Was it 0.9 c is 2.3 for gamma, something like that. So in other words, you have to get pretty close to the speed of light. But if you're going that fast, and so if Bob's going by that fast and Alice measures the length of his ship, it'd be about 1/2 of what he would get for that measurement. So let's write our two equations in general terms here because we've been using Alice and Bob with them. So let's do it like this. So we can say for the time dilation equation, we have delta t moving, okay? The elapsed time on a moving clock is 1 over gamma times delta t on a clock at rest. Okay, that's the so-called time dilation equation. Gamma being greater than 1, moving clock, the elapsed time on a moving clock is less than when it's compared to the elapsed time of an identical clock at rest. And then we can say, we'll say L moving equals 1 over gamma L, the length, a length at rest. So we're just transferring this, instead of saying L's above, we're saying moving and at rest here. So let's get rid of this and our analysis here, because we have a few more points to make with this. So this is the length contraction, so-called length contraction equation, so-called time dilation equation. Einstein actually wasn't the first to come up with these, as I think we've mentioned before. People like Hendrik Lorentz and Henri Poincaré were also coming up with similar results like this, but they were getting them in a very different fashion, and they almost seemed ad hoc results. They didn't seem to be coming out of the actual analysis. They sort of had to put it into their theory. Einstein is getting these results just from his two basic postulates, the principle of relativity, principle of light constancy. Put those together, and you discover that the speed of light is a constant, same value for all observers, no matter how you're moving with respect to speed of light. And then you started analyzing things like the light clock example and start getting these somewhat weird results here, that depending on how you're moving with respect to something, time, the elapsed time that you will measure, it will be different, and same thing with lengths as well. A little bit of terminology here. When we talk about, let's start with the length here first, the length at rest. In other words, if Bob is just sitting there in a ship, he's at rest as far as he's concerned. He's measuring his length of the ship. We call that sometimes the proper length. It's not the greatest term necessarily. In German, the German terminology for, of course, which Einstein was using, he called, I believe, his own length, just, own length. I think my German is really rusty, but I think it's Eigen. I'm not sure now. Anyway, own length in English, I know that much. In other words, it's Bob's own length at rest as he measures his spaceship, or whatever he happens to be measuring. And proper length has connotations of, okay, if this is proper length, another length we might be talking about is improper, and that's not the case at all. So it's the length measured at rest. And same thing for time. We could talk about proper time, or sometimes rest time. So that is the time measured on a well-running clock at rest. Sometimes some people like to call it wristwatch time. It's the time you would measure on the watch on your wrist. It would be a different time if you saw somebody's watch flying by and you're able to measure that, as we've been analyzing. There'd be the 1 over gamma difference in the two-time measurement of the times there. So some terminology there. One more question here. We actually asked this before when we talked about time dilation. Is this real? As Bob's ship goes by, what does Alice actually see? Right? Well, here's where we have to go back to the distinction we made early on in terms of observing something versus perhaps seeing something. And we defined observation using our photo principle. That an observation meant we had this imaginary grid or lattice of clocks, and at any given point we wanted to fix something, that something happened at that instant in time and space. We could take a photograph there, the clock would show it, all the clocks are synchronized in our frame, and we'd be able to specify the time and location in our frame of reference, and that's what we meant by observing something. The reason it's important is that if you talk about seeing something, then technically you have to think about, okay, if it's happening over there someplace, even though I have my grid of clocks and I can take a photograph out there and get the time, look at the photograph later, know what the time was and the location was. To see that actual event, I have to have light coming from it. Say it's a flash of light over there. I have to have the light coming from it back to my eyes, of course. There's a delay involved, and different things can happen if you have that delay, especially if you have an object moving past you. And involves an additional layer of complexity. It is possible to do that analysis, but it also gets a little confusing in terms of the basic concepts that we're trying to get across here. So these concepts are correct in terms of our analysis, and they're well supported experimentally. And if we talk about an observation being made in terms of our lattice of clocks and our photo principle, yes, it is absolutely true that a clock at rest will keep different time compared to a clock that you see moving along, and the length of something at rest will, if you put that in motion and then watch it go by, you will actually measure a different length for that. A little later on in the course, maybe almost the last week, next to last week or the last week, we'll look at this in a little more detail, because again, you can ask, do things really compress like that? If Bob is riding in his spaceship, does he sort of feel all of a sudden all sort of compressed? And you could also ask, well, what if there are multiple observers watching Bob, who maybe one of them is at rest, so he's going by at v, another one is going at half v, so he sees Bob at different velocity. Does Bob feel different types of length contraction? And the answer, of course, is no. Bob, as far as he's concerned, is at rest. And he doesn't feel any of this. It's the observations of other people making various determinations of the length that will depend on the relative velocity between them. But for now, we just have to focus on what we've got so far, our two big equations here, time dilation and length contraction. Again, elapsed time on a moving clock will be less than the elapsed time on an identical clock at rest by this 1 over gamma factor. And the measurement of a length will be less if you measure it while it's moving by the 1 over gamma factor versus if you measure it when you're at rest. In the last several videos, we have been considering that time is suspect. We found that for a moving clock, it runs more slowly than an identical clock at rest. We've also discovered that, according to Einstein's special theory of relativity, based on his two postulates, that length is also suspect, that, as we have here, length contraction occurs along the direction of motion. So if you have a moving object going by you, as you see it go by, and you measure the length of it as you watch it go by, you will get an answer, the length from your perspective, from your frame of reference, looking at that moving object going by, will be 1 over gamma, the length of that object, if it's just sitting there at rest next to you. Or if somebody is on that object, if it's a spaceship or a train car or something like that, they will measure one length for it, the rest length, sometimes actually called the proper length. It's not the greatest term because it sounds like that's the correct length and everything else is incorrect. But the proper length, or perhaps rest length, is the length of an object while it's at rest. Okay? And so if it's a train car and somebody's riding along in it, as far as they're concerned, remember, that's their frame of reference. They're at rest. They can get out the tape measure and measure it and get a length for that train car or spaceship or whatever. Somebody else, watching it go by and measuring the length as it goes by, will get a different answer. Different by this 1 over gamma factor, where again, of course, gamma is greater than or equal to 1. So the moving length is going to be shorter, usually just a tiny bit shorter, because gamma is very close to 1 until, as we talked about, you get up near the speed of light, but it will be shorter. So we have this length contraction effect. That perhaps raises the question, well, does everything change? Is everything suspect? Are there any quantities that are not suspect? And so that's what we're considering in this video clip. What is not suspect? And in fact, as an aside here, Einstein's theory has become known as a special theory of relativity, or the general theory of relativity later on, just the theory of relativity. And that wasn't his original name for it. He actually preferred invariance theory, that a theory of invariance, because if you actually look at the theory in more mathematically sophisticated ways, more advanced ways, it really emphasizes not the things that change, they're important, but really the things that stay the same from one frame of reference to another frame of reference. So theory of invariance. We talk about what is invariant. So really what we're considering here are a couple things that are invariant from one frame of reference to another moving frame of reference. And actually, in the next video clip, we'll consider something called the invariant interval, which will be important for us later on. So anyway, let's get back to this. So what is not suspect? We know time seems to be suspect in terms of synchronization of clocks and time dilation. Length is suspect as well. What about other quantities? And in particular, we want to look at the width and height of, we'll go back to our train car here. So here's Bob going along at some velocity v along these super fast train here. And we'll say that the length of his train car is L as he measured it. So that would be the proper length, the rest length of his car as he measures it. Gets out his tape measure there and does that. Here's Alice on the station platform. So this time Bob is moving. Alice is stationary. From her perspective, of course, from Bob's perspective, he's at rest. Alice is moving that direction, to the left, to his negative x direction. So let's look at the perspective of Alice, though. Clearly, from Alice's perspective, she would see this, assuming that the velocity is high enough that you get some gamma there significantly different from 1. So she would measure the length of Bob's moving train car as L moving times 1 over gamma, whatever the rest length was if he brought it stationary, and she could measure it there at the station platform. Then he goes by, she gets a different answer for the length. So now let's consider, let's do a top view first here, okay? And let's consider the width of the train car. All our analysis so far, really, we've been emphasizing just one dimension of motion along the x direction, but we're still emphasizing that as a direction of motion. But let's just imagine we can span it out just a little bit and consider width and height here. So here's the top view of our train car, Bob's train car. It goes along the tracks, some high speed v. And the question is there an effect there? We have a length contraction effect. Maybe as Alice looks at Bob's train car, maybe there's a width contraction effect as well. She gets up on top there so she can see down on top of Bob's car. Maybe there's a width contraction effect as well. So let's imagine there is this width contraction effect. So what would happen if it was a substantial enough effect? Bob's train car would contract as far as Alice is concerned, Alice observing the train car. And obviously, train wheels have rims such that this couldn't happen, but we'll just assume that it's such that as the train car gets shorter, less wide from Alice's perspective, what would happen to the wheels? The wheels would fall inside. Just imagine, the wheels are right here, of course, right there, there, and there on the tracks. But as the train car narrows in width, the wheels are going to be here, and they're going to fall off the tracks. Okay? And if it narrows enough, the whole train car would fall in between the tracks. Right? Obviously, there are railroad ties there and all that. But you get the idea that there would be an accident involved because Alice would see, if there is this width contraction effect, Alice would see the train car get narrower, it'd fall through the tracks that way. Okay? So that's what Alice would see, assuming this width contraction effect occurs. Now let's analyze it from Bob's perspective. Because from Bob's perspective, again, in his frame of reference, he's stationary. He's at rest. What does he see? He sees Alice, shooting back that way, but he also sees the train tracks going by him. Right? In his frame of reference, he's at rest. It's the train tracks that are moving in a negative x direction behind him. He's watching train tracks just constantly go behind him at a high velocity. Okay? Well, if the width contraction effect is true, it has to apply for this situation as well, right? Because, as we mentioned, the length contraction effect, the time dilation effects, they work no matter which perspective, which frame of reference you're seeing here. So in this case, if there is a width contraction effect, it's got to be true for Bob as well because he assumes that he's at rest, tracks are going by him, and maybe you can see what's going to happen here. If the tracks are what's moving with respect to him, and there's a width contraction effect, the tracks are going to get narrower. Okay? So in this case, get rid of these were our original, where the wheels were. For him, the wheels stay the same, his car stays the same, but it's the tracks that are getting narrower now. Okay, so the tracks in an exaggerated form. The tracks get squeezed in, and what happens? The train car goes off the tracks, but certainly doesn't fall through the tracks. It lands on top of the tracks, which are now underneath the car. So you have two very different conclusions. Alice would see the tracks get wider and the train car fall through. Bob would see the tracks get narrower and the train car would come off the tracks but would not fall through. You got to have one or the other. You could take a photograph. They both have to agree on the photograph that it happens, and therefore the conclusion is that there is no width contraction effect. Okay? That in that dimension, again, it's perpendicular really to the direction of travel. So the length contraction effect is only in the direction of motion. At least we just did width here, and we'll do height here in a second as well. Although another argument you could make here, physicists love to make symmetry arguments, and you could say if there's no width contraction effect, we're going to do height here in a minute. Well, you can just sort of rotate around. There really is no difference between width, height, whatever. It just depends on what direction you choose to be horizontal or vertical or whatever. So if there's no width contraction effect, by a symmetry argument, there should be no height contraction effect either, because you just as easily could define, okay, here's the width, or you could call that the height, and this the width, and so on and so forth. But let's do the actual analysis here for the height contraction effect. And so so that was the top view. We showed that if there's width contraction, you get two different situations in terms of what Alice and Bob observed. They both have to observe the same thing if you take a photograph, and therefore can't happen. Now let's imagine, going back up here to Bob along the tracks, say there's a tunnel coming up here. So we'll just sort of try to draw a tunnel like that. So going into the tunnel. To Alice, the tunnel is stationary. To Bob, of course, Bob is approaching the tunnel. So to Bob, the tunnel is actually coming toward him. He's at rest as far as he's concerned in his frame of reference. The tunnel is coming toward him. To Alice, the tunnel is at rest. It's Bob who's moving toward the tunnel. So let's analyze this situation, and let's assume that this tunnel is just the right height here from Alice's perspective. Okay? That if they were at rest, let's just put the train car at rest there, man. We slowly move it up to the tunnel. We say, hey, it will just fit. So the height of the train car is such that when everything's at rest, it just fits inside the tunnel. Okay? Now, what's Bob going to see, however? Remember, we just did the analysis with Bob, the train car. He's at rest. The tracks are actually moving by him. Bob sees the tunnel moving toward him at a very high velocity. If there's a height contraction effect, okay, so height contraction means height's going to get shorter, Bob's going to be very worried here, scared out of his wits. Probably he sees this tunnel coming toward him at a very high velocity, and if he sees the height contracted, he will see that he is not going to be able to get through that tunnel, or really the tunnel is going to smash into him. Meanwhile, what does Alice see? So Bob definitely sees a big problem coming ahead here, right? Alice sees, Bob, what are you talking about? Again, see, I'm using see in the sense of observe. Okay? Alice observes that there's a height contraction effect, but she sees the train car contracted, because to her, that's what's moving. If there's a height contraction effect on a moving object, it's the train car that's getting shorter. And then she says, hey, Bob, no problem at all. You have plenty of clearance to get through the tunnel. Well, again, clearly one or other thing has to happen when he gets to the tunnel, or the tunnel gets to him. Either he smashes into it, the tunnel smashes into him, or he makes it through. And therefore, since, again, you have this contradiction, you could, at that instant in time, you could take a photograph. You could decide, hey, does he make it through the tunnel? Is it too short? Is it plenty of room, even larger room, more height than we start off with? Again, both Bob and Alice would have to agree on that photographic evidence. So this conclusion is that there is no height contraction effect or height lengthening effect either. It doesn't go either way, so that height is going to be unchanged. It is not suspect. It is invariant. So when you have motion in one direction, there's a length contraction effect in that direction, but no effects in other dimensions. No effect on width, no effect on height. Those stay the same. So again, that's what is not suspect or what is invariant. And in the next video clip, we'll consider again, as I mentioned, something called the invariant interval that is another quantity that's invariant, not quite as simple as height and width, but we'll see what that is all about.